Hello everyone. Let me start with a little spark for your curiosity. Have you ever wondered how chemists manage to take something as simple as carbon monoxide, yes, the same toxic gas we hear about in pollution warnings, and turn it into a superstar in industrial chemistry? Well, that's exactly what happens in metal carbonyls. These are fascinating compounds where molecules of carbon monoxide act like tiny partners, binding to a central metal atom through coordinate covalent bonds. Some classic examples are tetracarbonyl nickel, written as Ni with 4 carbon monoxide ligands, and hexacarbonyl chromium, that's Cr with 6 co-ligands. Notice how the metals here, nickel and chromium, sit in lower oxidation states, almost as if they're relaxed and ready to accept electrons. And why do we study them? Because these compounds aren't just bookish curiosities. They play critical roles in industrial catalysis, in purifying metals, and even in advanced research labs. So, buckle up, because carbon monoxide is about to redeem its reputation in a very clever way. Alright, let's peek into their structures. If you picture metal carbonyls, you'll find they can wear different geometric outfits: tetrahedral, square planar, or octahedral. The beauty lies in how each carbon monoxide ligand attaches itself linearly through its carbon atom, donating a lone pair of electrons directly to the metal center. But the story doesn't stop there. The metal, being generous, sends back some electron density into the empty pi star orbitals of carbon monoxide. This two-way street of bonding is the secret sauce. For example, in tetracarbonyl nickel, the nickel sits at the center in a neat square planar arrangement, surrounded like a chessboard pattern. On the slide, you'll see the geometry illustrations, tetrahedral, square planar, and octahedral, that help us visualize these shapes. This dance of donation and back donation sets the stage for what we call synergic bonding. Now here's the real chemistry magic trick: synergic bonding. Imagine a handshake where both partners give and receive at the same time. Carbon monoxide first donates its electrons to the metal, forming what we call a sigma bond. But the metal doesn't just sit there quietly. It responds by pushing some of its own d-orbital electron density back into the carbon monoxide's pi star orbitals. This is the back donation step. Together, this donation and back donation form a strong, stable link. And there's a bonus effect. As the metal gives electrons to the carbon monoxide, the internal carbon-oxygen bond inside the co-molecule actually weakens slightly. You can even observe this in spectroscopy. The carbon-oxygen stretching frequency shifts downward. Isn't that cool? On screen, the arrow diagram shows this dual electron flow, one arrow pointing from co to the metal and another from the metal back to co. That's synergic bonding at its finest. Let's now explain this bonding through the lens of Valence Bond Theory. In VBT, the bonding depends on the hybridization of the metal's orbitals. Take tetracarbonyl nickel as an example. This means one nickel atom bonded to 4 carbon monoxide ligands. Here, nickel uses either sp3 hybridization or dsp2 hybridization to overlap with the lone pairs coming from the 4 carbon monoxide ligands. But what about the back donation? Valence bond theory accounts for it by suggesting that vacant d-orbitals of the metal can accept electron density from the carbon monoxide ligands, completing the synergic cycle. Notice how the electron count becomes very important. If the metal does not achieve a stable electronic configuration, the complex simply will not hold together. As you'll see in the orbital hybridization diagram for nickel tetracarbonyl, the geometry makes perfect sense once you imagine those hybrid orbitals pointing right at the incoming ligands. So, VBT gives us a first, fairly intuitive picture of how the bonds form. Of course, chemistry doesn't stop at VBT. The molecular orbital theory gives us a deeper, quantum-flavored explanation. Here we look at how the metal d-orbitals overlap with the empty pi star orbitals of carbon monoxide. This overlap creates new bonding and antibonding molecular orbitals. Because the electrons mostly occupy the lower energy bonding orbitals, the overall energy of the system drops, stabilizing the complex. It's like a tug-of-war that ends with both partners feeling more secure. A beautiful example is hexacarbonyl chromium, chromium surrounded by 6 carbon monoxide ligands in an octahedral arrangement. The MOT diagram on the slide shows exactly how the d-orbitals and the pi star orbitals interact, lowering the energy and explaining why these complexes are unusually stable. Now, chemistry students always love the part where we talk about isomers because it is like discovering the multiple personalities of a molecule. Metal carbonyls are no exception. They can show geometrical isomerism, such as CIS and trans arrangements of ligands around the metal center. For instance, in some carbonyl complexes, the 4 carbon monoxide ligands can either line up opposite each other, that is the trans arrangement, or sit side by side, that is the CIS arrangement. They can also show optical isomerism when the arrangement of ligands forms mirror images that are non-superimposable, just like your left and right hands. A classic example is zero-nonocarbonyl, written as iron to carbon monoxide 9, where 2 iron atoms are bonded to 9 carbon monoxide ligands. On screen, you will see a neat diagram comparing CIS and trans arrangements, which really helps us visualize how the same formula can yield different shapes. Isn't it fascinating how one set of ligands can make a molecule ambidextrous? Before we wrap up, let's connect this chemistry to the real world. Metal carbonyls are not just shiny molecules in textbooks. They are used as catalysts, for instance, in hydrogenation reactions that transform unsaturated fats into more stable compounds. They are also crucial in the Mond process, where nickel carbonyl gas, that is nickel tetracarbonyl, is used to refine nickel metal to extremely high purity. And yes, you will even find carbonyl complexes playing hidden roles in biological systems, binding to enzymes and influencing their activity. So, to sum up today's session, metal carbonyls are all about synergic bonding, a give-and-take handshake between carbon monoxide and metal atoms. Both Valence Bond Theory and Molecular Orbital Theory give us complementary pictures of this unique bonding. And the applications? They stretch from industry to biology. I hope this lesson helped you see how even a dangerous gas like carbon monoxide becomes a star player when paired with the right metal. Chemistry really does have a sense of irony, doesn't it? Thanks for joining me, and remember, chemistry is not just about reactions in a lab, it is the hidden script behind technology, industry, and even life itself. See you in the next class.